Okay, very welcome to all of you, and it's a pleasure that we have new students coming in new course for post graduation in physics, and our course is basically the quantum mechanical formalism. So we have to go through the quantum mechanics 1 in this course, and we will be discussing the mathematical formulation of quantum mechanics. But before we start our course, in view of the syllabus that's given to us, it's always better to first realize that why is it that we are going into the world of quantum mechanics. And that's not the only case. There is another important point, and that is we already used to have a formalism in physics, what we call as classical physics. And classical physics is a magical physics. It has given a lot to the world in all frameworks. It has given beautiful technology. It has taken us to moon. We can launch satellites in the sky using the laws of classical physics. So my point is basically that the advent of classical physics is very useful when you talk about the macroscopic systems. It works beautifully, and your predictions are accurate. You can accurately predict the motion of the bodies. And we have a range of subjects falling in the framework of classical physics. So that's our target. Our target is basically to realize what we can do using classical mechanics, what we call as classical physics. And then finally we will try to look into the limitations of this framework, because this framework is not a universal framework. Even though there is unification of theories, like you have the unification of electricity and magnetism, where you have the unification of the two theories into one formalism known as electromagnetism, which was basically done by James Maxwell. So we have a range of predictions. It has worked for us. It's working for us. The buildings that we design, the cars that run on the roads, the rockets that go into the sky, they all take the equations of classical physics. You make use of these equations to actually realize them in day-to-day life. So the intuition of this interaction with you is that I would like to interact with you. Rather, if you are in a position to interact, that will be a beautiful thing. That what we can do using what are the beauties of classical physics, and what are the limitations. So we will be talking about its foundation, its framework, and then finally we will try to constrain this subject in terms of its limitations that you can experience. So if I go on from here, if we have to describe what classical physics is, and you can see here that it describes the laws of motion and gravitation that are established primarily by Isaac Newton, and there are a range of mathematical philosophers who have developed this theory, like Newton, Galileo, James Maxwell. So you know all about all of these things before the advent of the quantum mechanics. So before quantum mechanics, what we had the classical mechanics. And we had a framework of classical physics that was running on in all domains. And what it does, basically, it deals with as I said, it deals with the macroscopic systems. I'm a macroscopic body as a whole. You are macroscopic. No doubt we are fundamentally made of atoms, but talking about the macroscopic systems, the classical physics has a lot to do, and it predicts, and the results that you obtain using classical physics, they are very consistent with the experiments, right? So talking about the historical background of the classical physics, roughly, these are the rough numbers, there's no precision in it. So it roughly developed between 17th and 19th centuries. And what classical physics did, it unified motion, force, energy into a coherent framework. Okay, so these were the fundamental things that could be executed using the classical physics. And the major contributions that were given, there are a lot more than them. To be precise here, I'm pointing out to these people like Newton, Maxwell, Galileo, and Lagrange. So, talking about the major branch, you already have gone through these courses. My intuition is basically to give you an insight of what you have already done, and you are all aware about these things, but the beautiful thing is that we would like to revise, at least from philosophical sense, that what we have studied. You already have gone through classical mechanics, thermodynamics, electromagnetism, optics, acoustics, and classical wave theories. These are the major courses that you already have done when you were in your graduation. So, talking about Newtonian mechanics. So, Newtonian mechanics, what it does basically, you have the Newton's laws of motion, and these Newton's laws of motion, they give you the predictions, they give you the technology, and all of these are coming when we code down the things to the macroscopic objects. So it's all plausible, it's all workable when we talk about the macroscopic objects. And we have the universal law of gravitation. Okay, the force of attraction between the 2-point masses is gmm by r squared. It's the product of the two masses, and it's inversely proportional to the square of the separations between them. So what it does, it explains how objects move under various forces in time and space. Now, these are the laws, the basic laws of classical physics, the law of inertia, as all of us understand what this law of inertia is, that a body will stay in rest or in uniform motion unless and until an external force is acting on it. Then we have the universal, the basic among the three is the second law of motion, which tells us that the force is directly proportional to the acceleration. Yeah. Now here, in the second law of motion, what is important is that your mass is a constant. So the mass is not varying. You assume that the mass of the object is constant. If the mass of the object is constant, then the force that you are applying on the body is directly proportional to its acceleration, right? And then we have action-reaction law. As we understand, as you will push a wall, the wall will equally push you back in the opposite direction. So these are the three important laws of motion, what we know as Newton's laws. And they are a foundation to understand the basic dynamics of the object, that how objects move, how long they move, with what velocity they move, what would be their at how much time a body will take to move from one point to another point. So there is another framework, that's work, power, and energy. They are all linked to that force and the displacement. If you rightly remember the definition of work, what is that? It's the dot product of force and displacement. So if you take the dot product of the two, that is going to give us the measure of the work. Now this work can be transformed into the kinetic energy. You can transform it into the potential energy. So these are the important parameters whose origins lie in force, basically. Okay, so the force makes a contribution at the basis when you define the work, and work is the product of force and displacement. Then you have the expression for kinetic energy. If you want to calculate the kinetic energy, you can calculate that using the equation 1/2 mv square, or v refers to the speed of the object, the speed with which the object is moving on. And then you can also calculate the power. For how much time you are doing the work will give you the measure of power. We occasionally, they are the building blocks of physical science. And what are they? These are the conservation laws. And conservation laws work when you deal with an ideal system. You imagine, you come up with an axiom, imagining an ideal system. In ideal system, you try to work out the conservation laws, like conservation of energy. So the total energy of the system remains constant. The total momentum of your system, if you have an interaction between the two bodies, body 1 and body 2. So their momentum, if the momentum remains conserved before and after. And these conservation laws, they are very central to the classical physics. They make a foundation to build the concepts in physics. So these laws provide the fundamental constraints. They provide the constraints, the objections on the physical system, because you would like to move from a perturbed system to an ideal system, from ideal system to the perturbed system. So they certainly play a vital role in the framework of classical physics. Okay, when you have a rotational motion, what you talk about then your linear motion translates into the rotational motion. So you have angular momentum. You talk about the angular momentum of the objects. Okay, so what they include torque, angular velocity, and the moment of inertia. They're all governed by this equation. Tau is the torque, and this torque is it's the product of moment of inertia and alpha is it's the angle, it's the angular velocity of an object that's rotating with respect to its axis. So what you have here is you have more in the framework of rotational motion, and if you got to talk about the rotations, you talk about the conservation laws. So there are conservations like conservation of angular momentum that is involved in rotational motion. And the most beautiful in classical physics is the universal law of gravitation. As I said, that between the 2-point masses you have a force, and that force is inversely proportional to the square of the separation between them, and it's directly proportional to the product of their masses. So this equation is a very useful equation. This equation is a basis to launch basically the satellites in the orbit. Using this equation, you can calculate the escape velocity of an object from the planet Earth, from other planets, from Sun, or maybe even a black hole. It may suggest us that why objects cannot leave the black hole. So to be precise here, this equation explains the planetary motion and the orbiting of the satellites. Now, another framework that you have already gone through is thermodynamics, but keep that thing in mind. This is all classical in nature. These are the courses that you have studied in the framework of classical physics. So here in thermodynamics, you have learned about the heat, you have learned about the work, you know about an ideal system and how you can transform heat into energy, energy into work, and you have a range of processes like isothermal processes, adiabatic processes. You have an example Carnot's engine, an ideal engine which has an efficiency of 100%. So that all falls in the framework of thermodynamics. And roughly talking about these laws of thermodynamics, the first law is basically the law of conservation of energy. If you rightly remember that, okay? Okay. Then what we have, can anybody among you tell me what's the equation for first law of thermodynamics?
Internal energy equal to work done plus U plus heat equal to internal energy plus work done.
Internal, but you gave the wrong definition, because when you talk about the laws that are governing our system, these things have no importance. The importance is only to the change. Is the change in internal energy equals what you said, heat and work. So it's all about the change, because the absolute quantities cannot be measured as well. They don't have even implications in our physical system. What has implication is in the change. So it's delta of that. Okay, you define first law of thermodynamics in terms of the deltas. Then you have the second law. It simply tells us the entropy of the universe is increasing. That means you will have more and more disorder is happening. It's going on, and a disorder of maximum amplitude is called what? A disorder of maximum randomness is, what is that called?
Entropy.
Yeah, come on.
Entropy.
A disorder whose magnitude is maximum. Now there will be no disorder. That's called, if I think it in terms of heat, it's called thermal equilibrium. So equilibrium is a saturated randomness. So if your randomness is extreme, you lead to the thermal equilibrium. Then you have this Zyork law of thermodynamics that already you already have studied this thing. And another important framework that we have gone through in your graduation is electromagnetism. And what you have done there is you talked about electrostatics. And in electrostatics, you have certain laws, the basic fundamental laws like Coulomb's law, Gauss's law is there, Gauss's law in magnetostatics is there, Faraday's law is there, a modified Ampere's law or Ampere's law. And then you have magnetostatics, another branch where you talk about the magnetism due to the flow of current. And then what you see that James Maxwell, he's combining the field of electrostatics with the field of magnetostatics and coming up with the four fundamental equations, whom we call as Maxwell's equations. So James Maxwell is able to, he was able to unify the two different frameworks, electricity and magnetism. And these four equations are very fundamental to the modern technology. They are fundamental to the transmission of the power. They are fundamental to the electromagnetic variations that are, because of those electromagnetic waves, we have the mobile phones, we have technology. So it's all coming from electromagnetism. Anybody carrying a phone, an Apple phone, it has its origins in electromagnetism. So this course also, you have already gone through this course. You have exclusively gone through this course in your syllabi during your graduation courses. And then optics. In optics, what we have, you have waves, and these waves interact. You have reflection of the waves. You have transmission of the waves. You have refraction of the waves. Okay, and here you have another strange observation that light is also a wave. When you perform that experiment on light, say the experiment of diffraction or a double slit experiment or Newton's rings, they are a confirmation of, they are giving us the confirmation that light is a wave, it's an electromagnetic wave. So this is how this classical optics works. It works, it explains reflection, why there is a reflection, why refraction, why diffraction, why interference. So we understand all of these things using classical optics. Acoustics is another important field which you have already gone through, and here you are mainly talking about the sound. Okay, so what you do here, you study the sound waves and you talk about the resonances, right? So the resonance is, what's resonance? Come on, yeah. If you have a wave A and you have a wave B, the two waves are superimposing on each other. What they lead us to. Now, depending on their frequencies, if the frequencies of the two waves match, they will make a maximum amplitude. This is what's called as resonance. So we have already studied these things like resonance, vibrations in the waves, okay? And these things are very key in the fields of engineering. Music, certainly music, it has a basis of putting the strings in the right mode at right time, leading us to beautiful music. And even medical imaging, if you talk about that ultrasound, it's based on sound waves. You're able to image the internal of a body using sound. So these are the implications of the acoustics that you have studied till now. And the basic governing equation. You have a basic equation that will give you the information about these systems in waves, is this second order differential equation. You have done it, okay? So what it does, describes the propagation of waves through the media. And it's important for sound, light, and water waves. You can describe the motion of these important parts like sound, light, and water. And all of these waves that generate in those frameworks, their origin is this second order differential equation. Now this V is dependent on what type of problem you are dealing with. So what classical physics does basically, it utilizes the main things in mathematics. What it does, it utilizes the differential equations. It utilizes the instruments of calculus, which was discovered by Isaac Newton. It talks about vector algebra to describe the motion and the transformations in your system, right? So this is the mathematical framework. This is where you have to open your wings. You have to open your wings to describe the systems using these mathematical tools. Now, another formalism that you have dealt with is Lagrangian and Hamiltonian formulations. Now, these formulations are basically easy formulations, because when you have to deal with the forces, it's always difficult to deal with the forces, because forces are vector quantities, and dealing with vectors is always a complicated thing. So you can deal with the same problems. Instead of using force, you can deal with the problems using energies, right? And certainly you know this Lagrangian is that you are writing down your equation of motion in terms of energy. So what it does, it provides elegant mathematical description of mechanics based on energy. You are doing the same work, the work that you are doing using Newton's laws of motion, right? You're doing the same work using a more elegant formalism, which you have already gone through, and that is Lagrangian and Hamiltonian formalism. And it is not based on force, it's based on energies. So you deal with energies in your equations rather than that of the forces. As I said, to deal with the force is a complicated thing. You cannot, it's very complicated to solve a problem based on a force, which is complex in nature. But the same problem you can solve by using the scalars, and the scalars here is the energy, and it is the foundation of the modern physics, dealing with Lagrangian and Hamiltonian formalism. Now, what are its capabilities, as I talked about in between when we were discussing about is, it is describing your macroscopic systems. Macroscopic, the big systems. The classical physics is beautiful, it's elegant, it can describe accurately your macroscopic systems. It has a tendency to explain the planetary motion, except a few like the motion of Mercury, which is resolved using general theory of relativity. But here we're talking about the classical physics. It's the basis for engineering, architecture, and astronomy. So all of these fields will not work if there's no classical physics involved in those branches of science, in those branches of engineering. And classical physics describes most everyday phenomena, the phenomenon that we can look at, the phenomenon that are macroscopic in nature. All of these phenomena are beautifully described by classical physics. So they're used in mechanical engineering, aerospace, thermodynamic systems, electromagnetic devices, optics and lenses. These are a few which I have tried to describe here. Otherwise, you will see most of the frameworks in the field of engineering are based on the classical physics. They make the foundation of it. So let's go down some important diagrams here, which I talked about, like force versus acceleration, potential. These are ideal systems. See how we do physics. We come up with an axiom. So what you do, you come up with certain postulates. Now, I should not go with the postulates. As a mathematician, I can see if I come up with certain axioms, I fit some of the rules. Okay? I fit some of the rules, I use these rules, I build an equation from these rules, and I try to describe a system. So the point is that if we see around us, can you find something which is purely ideal in the real world? No. But our physics starts with ideal systems. Now, talking about the second law of motion, what is it? It is force is directly proportional to acceleration, provided the mass of an object is constant. What does it mean now? It's an ideal situation. Can you tell me how it is an ideal situation? Yeah, come on. See, what am I saying? What is it saying? It's saying you apply the force, you will get acceleration. Is it true in the real world? Yes. Come on. Is it true? You should speak loud. It's true. In the real world. In the real world, it becomes true. But you start with this equation that force is directly proportional to acceleration. I'm applying the force to this. I'm applying the force. It's not coming in motion. I'm applying the force. So we are talking about an ideal system. We are assuming a system in which you are applying the force on a body and the body is not experiencing any other force on it. Under that circumstances, your force is directly proportional to acceleration. So you start with this ideal equation. Because when I apply a force to a car which is on the ground, maybe my force is not enough to move this car. So I am applying the force and there is no acceleration. Are you getting my point? I am applying the force and there is no acceleration. So what's going on? So the second law is telling you that in absence of any kind of opposition, you apply the force, you will have acceleration. That means you have an object in an ideal system where there is no friction, there is no air, there is nothing that can stop this object. But when you apply the force on it, it will cause acceleration. Now you can correct this equation, you can add the forces. Okay? Now, if you have to actually represent your formalism, you will add the forces acting on the system, and then it will accurately predict what's going on. But where from you are starting? You are starting from an equation which is not a reality in front of your eyes. Are you getting my point? Are you getting my point? So, you apply the force, you have acceleration. And then you have potential and energy curves. The oscillators, okay? Ideal. We start with an ideal harmonic oscillator problem. Ideal. It is undamped. There's no damping. It keeps on oscillating forever and ever. You have patterns in the water. You start with the idealism. You just, because you can represent things beautifully in mathematics when you have symmetry in your problem. So, this is force versus acceleration. This is second law of motion. Right? So, but it is true in an ideal situation. And when you come to the real situation, you have to add and subtract the forces so that you calculate the acceleration. You can apply the force on your system, and your system will have zero acceleration. Because there might be other forces which are cancelling my force that I'm acting on this body. So that's why, as an ideal equation, you have a straight line for the force versus acceleration, right? This is your ideal potential energy curve. It's ideally showing you what's going to happen to the potential energy of a harmonic oscillator. So this is how it goes. It has extremes. It has a minimum. It has a maximum. Right? And then you can incorporate the perturbations. You can incorporate the disturbances to your system. And you can again have the calculation. You can calculate. Talking about those waves, water waves, winds, tides, they are turbulent. They don't have symmetry. So what we do, we start with a symmetrical situation. We try to represent them using simple harmonic wave forms. What is it? It's a sine wave. It's a cosine wave. There's a periodicity in this graph that you can see about this simple harmonic waveform. You have one wave coming, intermingling with another wave. Now when the two waves intermingle, they can give you a maxima or minima depending on the phase. If the crest of one wave adds to the crest of another wave, you will have a maxima. If the crest of one wave adds to the trough of another wave, you will have a minima. So you have that symmetry. You have that ideal framework. When you use that ideal framework, you're able to talk about the complex things. You can explain why there is a bright fringe and why there is a dark fringe in a light experiment that we perform in the dark room. The same is the story with the Boyle's law. Okay, so you have the pressure. As you increase the pressure, the volume will go on decreasing. You take it as an ideal. You assume what you assume here. You assume here that the gas molecules have no size. You assume here between gas molecules there is no force. You assume here they are point masses. So it works. It works from limit A to limit B. But it will not cross the limit. It can explain your system up to certain limit. You cannot explain everything. There is a limit of explanation. That's what we have to realize. So, this classical physics, which I try to give you the brief overview so that your brain's fresh for this formalism. So it has limitations. It fails at atomic and subatomic levels. You cannot describe the non-radiating electron in an atom because it's against the classical electromagnetic theory. Any charge that accelerates will emit radiations. But that's not the case. So classical physics has a failure at atomic and subatomic levels. It has a failure near the speed of the light. When we talk about the special theory of relativity that was given by Albert Einstein, it fails when your objects are moving with the speed close to the speed of light. It fails in a situation where you are dealing with a black hole. A black hole is something which is massive in terms of the density of the matter. Even the light photon cannot escape this black hole. And how does gravity behave in vicinity of a black hole? It fails to explain that. What happens to time? Because for classical physics, time is an absolute physical quantity. For classical physics, mass is an absolute physical quantity. Right? And it strongly fails in quantum phenomena because we have to go through quantum mechanics, so it fails there also. Now I think here we will stop, okay? If you have any queries, because tomorrow I'll take